Okay, here's the second video on energy. I want to talk about something called the state function of energy, which in the book it describes it as essentially saying the energy change in the system does not depend upon the intermediate steps that it took to get to accomplish that change. Uh, and I want to demonstrate this a bit by I'm going to take a really simple system, and then I'll cover a more complex system involving chemistry. But a simple system here, it takes this chessboard. Imagine we have a piece down here in the corner of this chessboard that it's like a king that can't move diagonally. So this piece can move vertically one square at a time or horizontally one square at a time. Okay, and the goal for this chess piece is to get to this opposite corner. Okay. So the question is, well, how many steps does it take, and does it matter which direction you go? So so you can start by saying, well, let's just do one way. Which one way would be go, like, let's say, go all the way to the top, and then turn right and go all the way to the end. Well, let's count the number of steps. It's basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Well, I wonder if this system is a state function. I wonder if it matters what path we go. Is it always going to be 14 steps, or could there be a different way of going? Well, I think you can quickly mentally decide, yeah, this is a state function. But you go through another example, you can see, imagine we went this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That one's 14 also. And you can quickly prove to yourself that, since you can only go vertically or horizontally, it's always going to be 14 steps no matter what. It turns out the energy in a chemical system works exactly the same way. And I'm going to demonstrate that. And this is an incredibly useful aspect of chemistry, the fact that this is true. And you'll see that as we go forward into describing Hess' law and everything else in this chapter. So let's take an example like, imagine you have carbon, basically a lump of coal, and you react it with oxygen to produce carbon dioxide. Okay? And let's say this is a gas, and this is a solid, and this is a gas. Okay? Okay, so you can imagine that there's definitely an energy change in the system here. And in fact, this particular type of reaction, because it's burning carbon, actually produces energy. So the way we write that is we basically say that this reaction has a delta H of reaction equal to a certain amount of energy. Okay, and the energy, let's say that we calculate or we look up in a book, and it says it's minus 310 joules per mole. Okay, which is essentially saying that if you had a mole of carbon and obviously a mole of oxygen, because there's the same coefficient, and you reacted them in this way and produced a mole of carbon dioxide, the amount of heat released, or the enthalpy change of the reactants, but essentially the amount of heat released would be would be 310 joules. The minus sign just means that heat is transferred out of our system to the surroundings, meaning we're generating heat. Okay. The opposite of this would be let's say, well, another reaction that had a plus sign here would be a reaction that requires energy to suck in from its surroundings, meaning you'd have to heat it up to result in the reaction. Okay, so those are the two different types of change of enthalpies in reaction. One is called exothermic, producing energy. The opposite is endothermic, meaning requires energy to complete the reaction. Okay, now back to the main point about state functions, though, is that imagine instead of this reaction, we burnt carbon with a half a mole of oxygen and produced carbon monoxide. Okay, which would this happens in a case when you're burning something and you don't have as much oxygen, you actually partially combust the carbon, and in this case make carbon monoxide rather than dioxide, which obviously has got its own problems. But then we went on, let's say that we took all this carbon monoxide and we then, in a second step, burnt the carbon monoxide, again with a half a mole of oxygen, and produced carbon dioxide. Okay? Each of these is going to have a delta H. Let's say this first delta H, when measured in a lab, comes out to be minus 160 joules per mole, which essentially means if you burn carbon with not enough oxygen to fully combust it to carbon dioxide, and you instead make carbon monoxide, the amount of energy produced is 160 joules per mole. But then we want to say, all right, well, on the second reaction, what's the delta H of this? Well, it turns out we can make use of the fact that energy is a state function to know that the energy produced in this step, when added to the energy produced in this step, must equal the energy in this step. Because again, if you add these reactions like we've done when we're doing our stoichiometry, you'll see that when you add these up, you end up with carbon plus 1/2 oxygen and another 1/2 oxygen, meaning a whole oxygen, plus carbon monoxide, but of course carbon monoxide is on the other side as well, so they kind of cancel. This, when adding these two together, you end up with the exact reaction we have at the top. It's essentially a different path of getting from carbon and oxygen to carbon dioxide. You're going to get there directly like this, or indirectly through an intermediate step. But we can make use of the fact that energy works as a state function to actually, knowing these two numbers, 310 and 160, we can calculate this one, and you can do the math and see that it has to be minus 150 joules per mole. Essentially, you take both these reactions and you'll end up with minus 310, which matches this. So we're going to make use, so this is just a demonstration of what the state function means. We're actually going to make use of this concept in some valuable calculations that happen in the next video, I think. I do want to finish off a couple of other comments here before I go on to the next one, though. And that is, you see that I made a notation here, delta H of reaction is this. And what you'll see is that on delta H's in the book, even in other places, you'll see the subscript that essentially describes the change in enthalpy due to what? Due to what kind of process? In this case, it's due to a reaction that I've drawn, a chemical reaction that I've drawn. But there's many other common and important delta H's that we'll encounter. I want to list a couple of those and describe them. One in particular is very useful that we'll use quite extensively in the next video. Okay. All right. So what are the sort of system changes that can result in a change of enthalpy? Well, you can have a change of enthalpy due to vaporization, for example. An example would be water as a liquid goes to water as a gas. Okay, so this is going to this is essentially boiling water. Okay, here the delta H of vaporization for the water is plus, I don't know what the number is. I'm going to make it up, plus 120 joules per mole. That's not the right answer, but or what right number. But I'm throwing a number out there for grins. I want to show this plus because in order to make this change happen, we have to add energy to the system to boil the water. Okay, so that's a very common delta H that you'll see in books, which is the enthalpy change due to vaporization. Okay. Similarly, you'll have there's a similar one, which is the delta H of fusion or melting, one or the other. Fusion is essentially water as a liquid becoming water as a solid. It's fusing. The liquid water is fusing. This actually will have a delta H that's minus because when a liquid freezes, it has to give off energy to do that. The reverse, which would be the melting, this were S and this were L, that's delta H of melting. You almost never see that though. They usually use the fusion one for this. But they're the same, it's just that the melting one has a different sign And so the melting would, instead of being a minus, it would be a plus, meaning it requires energy to melt the water. Okay. So vaporization and fusion are common ones. There's also delta H of ionization, which essentially means taking something like sodium metal and changing that, removing one of its electrons. So turning this now into sodium cation plus an electron. So this always requires a positive enthalpy. You've got to put energy into the system to ionize, to remove an electron from an atom. Okay, so you'll see that one quite a bit, and we'll see that one a lot when we get into the later chapters too. But lastly, and probably the most important one, at least for the next video, is a delta H known as formation. This actually can apply to any substance. For example, let's say carbon dioxide. So the example would be delta H formation of CO2 is essentially the same as the enthalpy change in a reaction of elemental, same one I was using before, actually, same one I actually have magically drawn right below here, which is to make carbon dioxide, you take its elements in their natural form. In this case, it's solid carbon and it's gaseous oxygen producing gaseous carbon dioxide. The delta H for this reaction is also known as the delta H of formation of CO2, because this reaction is using just the elements involved in the product that we're interested in. Okay. Now the delta H of formation becomes a really strong concept that we can use to solve some problems that we'll do in the next video, but also in kind of making quantitative statements about how much energy is stored in a compound, in a chemical. Okay, and again, how much energy is stored can be valuable to know. If you burn it, it's going to produce energy, or to make it would require a lot of energy, or those sorts of considerations. Okay, I'm going to end this one now.